Hey guys, welcome back. In this video, we got cell potential and concentration. All right, but we're going to start off with cell potential, which of course is cell potential. All right, it's E standard, standard reduction potential, and then free energy, which is delta G standard, and how they're related. Well, we know a volt is a joule per coulomb. All right? Which comes out to be work over charge. And I think we've covered this before, kind of. We're going in a little bit more detail. All right? So now, work, all right, which will equal E standard, right, which is in volts. And so work, write it down, work equals what? Charge multiplied by E standard. Oh, it didn't change color on me. Sorry about that. Times E standard. All right. So now the charge is going to be what? Number of electrons transferred. So we're going to break this down. So the work out of this is delta G standard. That's the work. The charge is going to be negative N for number of electrons transferred. F E standard. All right. So this is the maximum theoretical work. We get out of the cell. We have moles of electrons, that's an E, electrons transferred. We got, of course, 96,000, well, I'll bring it up, 96,485 coulombs per mole of electron transferred. And then our standard reduction potential. So in our cell, right, which is the Daniel cell, we had Zn, Zn2 plus, Cu2 plus, Cu, and that E standard is 1.10 volts. If you remember that, your note should have that, right? And we know that there are 2 electrons here and 2 electrons there, right? So that means N is 2. So for this cell, delta G equals negative NFE. And it's delta G standard. So that means delta G standard equals negative 2 moles of electrons times 96,485 coulombs per mole of electron. And we have 1.10 volts. Now remember, that's the same thing as 1.10 joules per coulomb. So the coulombs will cancel, and the moles of electron cancel, and you're left with joules. So if we do this math, delta G for this would be negative 212 kilojoules of work that could potentially come out of this cell. That's kind of cool, huh? Right? So we can figure out how much work we can do with the cell potential. Now, the next question, though. And because we have this guy right here, this word, concentration, what's going to happen with this cell after it runs for a while? And you kind of fundamentally know this, right? You might have devices with batteries. A flashlight's a great example. Whether it's a rechargeable battery or a non-rechargeable battery, you get a flashlight, and after a while, at first that flashlight is just bright, it's nice. But after a while, and we don't notice it, but then all of a sudden we do notice it, it's not as bright. It's just not as bright. Well, why? Well, we know the battery's running out. Okay, but it's not running at 100% the whole way. It's dwindling. It's percentages. So it's 100% brightness, that flashlight when you first turn the battery on, and then as you go and use it, it just gets a little bit dimmer ever so much. So as you move on, to finally you notice it. Yet it's still going, but you notice it, right? And so that leads us to this cell potential and concentration. How does the concentration of the reactants in the products affect the cell potential? All right, good question. And that relationship of cell potential and concentration is the Nernst equation. All right. So we have standard conditions, delta G standard, negative NFE standard, and non-standard conditions, delta G equals negative NFE. Now, it doesn't matter E. All right. Okay. So now, to derive this, we're not going to do this. I'm not going to do that to you. We're just going to have E. This would be the observed cell potential. All right. Is going to be equal to E standard. All right. And then we're going to have minus R T N F times the natural log of Q. And Q, of course, is the reaction quotient. All right, so that's our Nernst equation. All right, so once I get this written, so that's what we have for cell potential and concentration. Let's do an example. So let's say our battery, our Daniel cell, has been going on for a while. All right, and the concentration of copper 2 is reduced from 1 molar to 1 times 10 to the negative 4 molar, and zinc is basically 2 molar. What's the cell potential? All right, wow. All right, so we got what's the cell potential? So we have the copper is that, and the zinc is that. So I like to write out the equation. Zn solid plus copper 2 plus going to copper solid plus zinc 2 plus. Q then would be zinc 2 over copper 2, right? If we do our reaction quotient that way. N is still 2 moles of electron, right? So we're going to do the Nernst equation. E equals E standard minus RT NF ln Q. And let's write this out. We're looking, E is, I don't know. E standard is still the 1.10 volts. R, what are we going to use? Well, I do not have molarity, so I'm going to probably use the 8.3145 joules per mole Kelvin. Temperature, we're going to assume 298 Kelvin, unless otherwise told. All right, and 2 moles of electrons. F, 96,485 coulombs per mole. And then we have Zn, 2 plus, is 2 molar. And Cu, 2 plus, is 1 times 10 to negative 4 molar. So that's all of our variables. I think we can solve this, can't we? All right. I think we can solve this. All right. Now, what you would probably do if we were going to do this, I'm just going to take this equation and bring it down. Whoa, not that far. All right. And I'm going to erase this right now. And so what we would have to do, right, in this is you would write your Cu2 plus 2 electrons going to Cu, and that standard potential is 0.34 volts. Then you would have Zn going to Zn2 plus 2 electrons going with that potential being now positive 0.76 volts, right? And then you would add them up to get this Zn solid plus copper 2 plus, and I would sometimes it's a good idea just 2 electrons, making sure that these work. All right, and your cell potential. Now, you're going to have to do that. We didn't because we've been using the same example as we've been going on, but you're going to have to do that, all right? So now we can plug this all in to our wonderful equation right here. All right, so we're looking for E. We don't know what E is. E standard is 1.10 volts minus 8.3145 joules per mole Kelvin, 298 K, 2 moles of electrons, 96,485 coulombs per mole, times the natural log of our, what we got? Well, zinc is 2 molar. And copper was 1 times 10 to negative 4 molar. All right, so if we do this, I get 0.97 volts, which is pretty neat. So now, eventually, the cell potential will reach 0 at equilibrium. You knew it was coming, didn't you? You knew that word was coming, all right? All right. So at equilibrium, E equals, I put E standard down because I was thinking E equals 0, not E standard. E standard is E standard, right? It's at 25 degrees Celsius, 1 atmosphere, 1 molar. All right. E can be 0, and Q equals K. All right. And so if we put this into the Nernst equation, 0 equals E standard is RT and FLN K. So that means E standard equals RT all over NF natural log of K. Now with this, that is, right, standard cell potential and equilibrium constant. We also now have delta G standard equals negative NF E standard, right? And we have delta G standard equals negative RT natural log of K. So we have all those. So if I have a standard reduction potential, all right, if I have electron transfer, I can have delta G or if we have equilibrium. All right. So if there's electron transfer, all right, I have two options. If there's not electron transfer, I have also two options. So I got the free energy change, I can get the equilibrium constant, I can get the cell potential if there's electron transfer. Right? If I have an equilibrium constant, I can get the cell potential and vice versa. So we have all that. All right. So these are three equations to definitely have written down. All right. They're on your sheet, but definitely have them written down. Okay. So that is the Nernst equation. That's a big one. We were going to do some more examples, but if you have any questions, reach out. Otherwise, we'll see you next time. Take care, guys.